So what we're going to be talking about in this is instrument to inference architectures. And I want to do a little bit of explaining what that means before we actually go and do, the nitty gritty. So what I'm talking about here is if we have, a spacecraft, right? And we have a camera and we have, some planetary surface, right? So the instrument to inference is as it sounds, is we're trying to go from here to some sort of information that we get out of that observation, right? And this is distinct from the data itself, right? So the data is transmitted, right? And you do some analysis. And, this is the first time in obviously my career and recent history that we've been really, really focused on automated pipelines for this process. How can we automate this to this, this to this, to this to this, so on. But in this new era of machine learning, what I'm interested in is how can we go from this to this, right? So how can we do instrument to inference? How can we build automated end-to-end pipelines, right? That will take spacecraft data and, like that faster than, we could even pay someone to do it, give us a scientific output that we can use to make decisions with confidence metrics as well. And one of the big challenges with this, which we'll talk about, is that in order to build something that goes from the spacecraft, builds the data, right, and then does the analysis, and then, does the inference, you really have to spend a lot of time understanding this process right here, right? So what are we trying to study? How are we going to study it? And then, what inferences can we gather from it? And so a lot of what I'm interested in is to facilitate this gap in the process. What we ultimately need to do is build databases that have a lot of tagging that make it very obvious to build a model that has all of the context that you would need to build an inference, and we'll explain why that's important. But just understand that what we're talking about here is building the infrastructure necessary to have automated end-to-end data interpretation pipelines. And this can be for science, for reconnaissance, for defense, for computer vision, for whatever you want it to be. The goal here is to make going from an observation to the knowledge that we get from that as efficient as possible. We're live. They're going to get some spoilers. I wanted to do a 10 to 20 minute, hopefully this doesn't turn into 5 hours again, where we talk a little bit about instrument to inference architectures. I have a meeting on Monday that could turn into a new opportunity if we play our cards right. So I wanted to make sure that I am well practiced at explaining things. So I assume if I need to start learning how to record in bytes and then save it in a way that I can easily edit very quickly, because that last one took way too long. So I'm gonna hold up a 1 in front of it or 2, and try to do something to organize my takes a little bit better, as well as name them. So I'm gonna stop this recording and then we'll start from there. So before we get into kind of the nitty gritty of instrument to inference architectures and that concept, I want to share. Let's close that out. A talk I gave for a different context that helps kind of motivate the purpose for this. So this talk was particularly focused on explaining the progress that we've made on one specific type of model that we think could be used in one of these full end-to-end pipelines, right? But I think it does a good job of kind of motivating the problem and why it's important that we have automated pipelines. So in terms of hyperspectral image classification, a lot of the methods that you see used in the last 5 years and first order are neural networks, convolutional neural networks. So to kind of talk through this, we're going to use an example data set called Samson. It's a hyperspectral image that has 95 pixels by 95 pixels and 156 bands of data, right? So that's 156 different parts of the electromagnetic spectrum. You can think of RGB as red, blue, and green, red, green, and blue, and that's 3, and this is 156 of those colors just spread. And the model that we're going to be focusing on is called AUSSC, the Alternately Updated Spectral Spatial Convolution. This is by Wang et al. 2019. I'll put the paper below. And it's essentially focused on trying to minimize the amount of ground truth, and it's what I'm using to kind of explain this problem. So in this data set, we have 3 different classes of materials: soil, tree, and water. It's a very simple data set. These interpretations of what that spectra are very first order, and it's really just designed to be a really good demonstration of data analysis pipelines. And so there's a website that has a lot of hyperspectral data as examples like this, which are really helpful for machine learning papers and studies. So what we're going to do here is we're going to downsample our data, because 156 bands is a ton. And you're going to understand why, particularly because our goal for this model was to do domain translation between low and high resolution data. So that's why we're doing this downsampling, and we're downsampling to match the Worldview 3 data. And this is what that end-member spectra looks like with the full 156 bands, right? So we're down to 16 bands now when we downsample. And we also have ground truth abundances. So for every pixel that's a spectra, we also have an abundance value for each of these 3 classes. And that's the key, is there's a lot of information that is built into this data set that we can use to train a model. So some of the loss statistics that we're using here, it's not super important for y'all's context, but we're using a softmax cross entropy function, which is essentially increasing the interclass distance, while the center loss is a measure of the similarity within the class. So it's decreasing the intra-class distance. So, to distinguish classification, to classify something, you need to distinguish the groups, right? So this is talking about how we're separating what those groups are, and we're shrinking what those groups are represented by. And in the end, we can get these predicted classification maps. And what's cool about this is you can actually see the training happen, which I quite like to witness, especially for the context of the spectra, which we'll notice in a little bit here. So AUSSC makes a lot of improvements on traditional CNNs to try to minimize the dependency that we have on that ground truthing data. And it's still, unfortunately, depending on over 200 spectra that have that class or abundance label. And you can see that it falls off in accuracy quite significantly once you hit that point. A traditional CNN will have accuracy of around 75% with only 200, while AUSSC can hit around the 90 or above, but still 200 is a lot of labels for you to gather the context of for every kind of question you want to answer with a particular data set, right? So it's, and this is with ideal data as well. Like, we have very, very well-honed classifications. This is a really well-studied, it's an ideal data set. So if we're talking about the real world and the real data, it's not going to be this simple. And this is one of the most highly optimized, supervised methods that we, I can't say that we have to date, because I haven't done a full, heritage review, and things are changing so quickly, but it is one of those methods that's really highly optimized in comparison. So it seems like the largest gap limiting frameworks for machine learning of hyperspectral data is the ground truth. We have high volumes of unlabeled data, and that training data has to have the spatial spectral variability, all of the compositional, physical, chemical, environmental, thermophysical, instrument, geometric factors, the response function, blah, 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 blah. All of the context has to be in that label for you to be able to build an inference off. The ground truth has to reflect the desired inference. If you want to infer something about the composition, well, your ground truth data has to be compositionally related. It has to have abundance data, for example. And that's the biggest challenge. Guess what? You just created the entire field of remote sensing. You're not automating anything. You are spending most of your time building a data set with labels that you then use to train to do the inferences that you could have done with that thing you made to begin with. So this is one of the big challenges with kind of pushing the paradigm, and we're motivated to do this because there's kind of a new growth and a motivation to transition from multispectral to hyperspectral so that we can get that extra bit of information in addition to pushing the spatial scale down. Right? So couldn't we just use the methods we did to create the ground truth to do the inference? It seems like it's more work than just the traditional means. We couldn't possibly pay a spectroscopist to do this, right? So instrument to inference architectures is referring to the goal of creating onboard, on-demand pipelines for identification, detection, classification, mapping, and quantification of hyperspectral image data. To get to that inference, you want to hit every step of that process so you're getting the full context. And for it to be worthwhile over traditional analysis, the models need to be on board and on demand. So we have to reduce the data throughput. We have to send inferences instead of full hyperspectral image data. Because if you had hundreds of these assets taking thousands of pictures a day of all these different regions and different timescales and different compositions, there's absolutely no way the data could ever be useful. So the saturation of information, saturation of data tends to make it harder to get information out of things, right? And so it needs to be automated end-to-end and resource efficient, right? We can't be shipping GPUs up into space, right? So we need to be able to send back the smallest amount of packaged data that we can, or send back inferences. We also want minimal deployment requirements, right? So we want something that's pre-trained that we can load up onto a onboard computer that won't be dealing with a lot of restrictions that would then limit the engineering of the spacecraft and the instrument itself. So let's talk about that. How do we do, instrument to inference? Well, we have to answer some questions. Well, how do we know what to look for? Well, so we can do something like generating synthetic spectra or doing super resolution of spectra. And we're going to talk about UV-Cgon and VAEs more in a little bit, but those are some models we're exploring for those kinds of questions. How do we match the expectations with the observations, right? And we use end member targeting for that. So how do we know what kind of thing we're looking for that we then want to classify to? And answer the question of what is the target material? What is the context that it's sitting in, right? We want confidence qualified detection. So we don't just want to know it's there. We want to know how much of it is there, and we want a confidence metric for it, right? So some of the ways that we're going to be addressing these last three ones is using things like GCNs in order to fill in the gaps. We hope to look into INRs for a similar problem, AUSSC for situations where we do have ground truth, but it's not a lot. And what we're going to talk about a little bit more later is GONS in general, right? And then we want to do mapping. So we want to add that spatial component, that temporal component. Where is it occurring? When is it occurring? And we want to do unmixing. So we're going to reinforce our interpretation by doing an unmixing analysis of the abundance, the mixture of abundances, things like particle size, whatever condition that you want that might be complicating the interpretation, right? So for the context of spectra, for example, you can have a thermal infrared spectra of one material and it looks completely different if its particle size is just a little bit smaller, if it's being observed in a vacuum or not. You can have massive differences that we still don't understand the fundamental mechanisms for that can be introduced that you need to be able to contextualize, right? And then with that, you want to be able to answer the question of how much is there. And this is where we get into things like multi-attention and conditional GONS that would pull as much information as you can out of a fully unsupervised method. So these are those different models that we're focused on, and I've highlighted some ones that we've working on, some of the things that we've attempted, and the plans that we have to explore combinations therein. And the key here is that you kind of have two different ways of doing it. You can derive your inferences, you can do this process by deriving it from data inferences, like so the ground truthing, right? So we know that this material looks like this in this instrument, and so we just build a database of that and train the model on that, right? Or you can do modeling of fundamental mechanisms. So why does the instrument think it looks like this? Or why is that observation the case? What about the context is affecting it? How does light interact with that material that's resulting in this signal? So our best guess for light matter interactions, things like Hapke, Sherkatov, thermophysical analyses, so on, right? This, on the other side, it's a whole other paper and kind of study. It's a whole talk in itself that I'm not going to get into right now. But the key is that we have to use both to make better inferences and to improve our understanding of the fundamental mechanisms, right? So they kind of feed off of each other in that sense. We're going to focus on how we derive from data inferences, which includes collecting labeled data across those different contexts, right? And unsupervised and self-supervised learning, right? So we'll comment on that towards the end when we start to get into kind of the databases and the knowledge databases. But we're going to focus on unsupervised and self-supervised learning, right? So it's really only going to be feasible through a combination of semi-supervised, unsupervised, and self-supervised methods, right? So the method that we talked about earlier, which was semi-supervised or supervised, right? And to be clear, when we talk about supervised, we're saying that we have a target label, we have a prediction, and we use a loss function to compare those, right? So we have ground truth. Semi-supervised is, just a little bit of ground truth data, right? So AUSSC might be a good example of that if it was combined with some other kind of unsupervised method. Unsupervised being a method that creates classes and clusters without having to compare to something, whereas a self-supervised method will take unlabeled data, build representations of it, and use that to create its own labels that it then uses for context, which we're not going to get into much today. So we started evaluating the use of VAEs, which are variational autoencoders or disentangled variational autoencoders, to do that fully unsupervised classification, which is basically looking at whether we can use the most fundamental representation of what makes data variable to distinguish clusters in that data. So you take that input data, you use an encoder to bring it to a latent space, which is often regularized, and then you bring it to a decoder, which is then reconstructing it, right? And can you use that latent space to understand what makes that data significant, right? And so if you take all of the soil spectra from Samson and we apply our VAE to it, it might help us figure out where variability is occurring in that data set, right? So you might notice here that we can see particular locations where there were differences or large fluctuations or outliers or whatever it might be. So it can kind of help us target other models, right? It can cluster data ahead of additional classification tasks. It's a very simple foundational method, right? And the model is learning on its own that these bands are significant to the abundance differences because they're significant to reconstructing the data, right? It's saying, after looking at all of this and after doing this encoding, decoding process, I now know that the data generally will look like that. And it knows then what was important to do that reconstruction. Well, this region here was important, or this was here because of this, and so on, right? So it essentially does that by figuring out where it's difficult to reconstruct. So wherever it's difficult to reconstruct, you're going to have the most variability. So you can use that to target things like abundance variations, for example. So there's a lot of different ways autoencoders are helpful, but we use it for pre-training tasks, which is why it's introduced here. But the key here is that you're performing pixel-wise reconstruction. It's very noisy. It tends to really only capture the very average representation of that data. So it's going to struggle with diverse groups, subtle, nonlinear changes. So now we're going to talk about GANs, generative adversarial networks. These leverage adversarial training to learn directly from the data distribution rather than doing a reconstruction. So you can imagine it like a generator, who's the artist, who looks at a real data set, this painting of a duck, right? And they try to make their own duck. And then you have a discriminator who looks at the real data and then looks at the painting and goes, okay, that looks like real data. Right? So it's a game where the generator is trying to trick the discriminator. So, no, I made this, I tricked you, I win. Right? So that's the process. And if the artist wins, the loss goes down. If the discriminator wins, the loss goes up. So GANs better represent the full distribution of the data and its details because you're not encoding and decoding. You are building from the ground up iteratively until you approach a accurate solution. And what's cool about this is they can learn to produce data from completely blank noise, generate relevant data, or they can convert between data types. You can take a chicken and turn it into a duck. If the artist, instead of starting with a blank canvas, starts with a chicken and then it's forced to form a duck, you have now learned how to translate between those different types, which is really cool because now you can transfer between different contexts, different dimensional spaces, entirely different species in this case, right? So this begs the question, can we use this to generate ground truth data? Can we translate results from the lab to the relevant remote domain? And that would be really helpful, right? Because if we can do that, then an inference we make in one domain, we can now transfer to the other as long as we understand their differences. We can take well-constrained data from the lab, low-fidelity observations from the field or on orbit, right? Spectra, for example, low and high-resolution spectra. And we can bypass the challenge of creating ground truth in the context of the spacecraft, and we can instead change the domain of data that we have that is conveniently ground truthed. So if we're trying to make a inference about composition and we don't have ground truth of that spacecraft data for this composition, but we have a bunch of samples in the lab that we know are relevant. We know at least they're similar compositions. They're just different observation domains, right? So I can study my lab data, apply an abundance measurement to what that spectra looks like in the lab, translate it, and then use the same methodology as a proxy for abundance on orbit. This is really valuable, but also really dangerous as a scientist, and I'll explain why later. So we are going to demonstrate one-dimensional data translation between the lab and remote domains. Because to know what to look for, going from lab to remote, and what we're looking at going from remote to lab, we want to have both. The translation needs to be reversible. So a GON is not sufficient. A GON can only go in one direction. So we need a cycle GON, which uses a second pair of generators and discriminators, so a whole additional one going in the other direction. So duck to chicken, chicken to duck, right? And this ensures the reversibility of domain translation. You have one GON for A to B, another for B to A, right? And you can see how this would allow you then to go and learn how to generate a duck from a chicken, and then take that duck you made and go back to a chicken, and the reverse. And then you can look at the start and the end, and you could say, oh, are these consistent? You go from A to B back to A. What does the first A and the second A, how do they compare? How well did you reconstruct the original domain? Cycle consistency loss is thus used to translate back to the input domain, right? So now you have a two-way translator, right? And then you use identity loss to preserve the domain-specific features, right? So cycle consistency loss is comparing duck 1 to duck 2 and saying, how accurate are you, right? What's happening here is it's saying the domain-specific features in the source, are they preventing me from getting to the correct domain? And the way we do that is we actually apply the generator to the original domain that would take it to itself. And if it doesn't change things, then it's good, right? So let me phrase that, because I think I got a little stranded in that explanation. The identity loss is going to take, for example, a duck and place it through the chicken to duck generator. And if you come out with something that doesn't look like a duck anymore, then your identity loss goes down. Hopefully that's more clear. So you could do things like this. You could translate a horse to a zebra, or a zebra back to a horse. And this is actually from the original paper of CycleGon as a demonstration of what they can do here. But you also have examples like this where as I mentioned, identity loss is a way for you to prevent unwanted changes in the original domain's features, right? And, they're not going to be perfect. You can have situations like this. So CycleGon shows promise in doing domain translation between low and high resolution spectra. And we've demonstrated a 1D model that will use GON's utility in this before we move on to 2D hyperspectral data sets and so on. So this is what that looks like. You can see the red line is the generated spectra. It's slowly forming to match the real target equivalent. And this is, again, we're going from high resolution to low resolution data. We are domain translating from something that is 156 bands to something that has 16. And it's showing what the material would look like if you viewed it remotely. It's essentially doing the compression and all the differences due to observation conditions. It's accounting for the spacecraft's instrument response function and atmospheric aberration and all those other kinds of things. We can go back. So we can take that remote spectra that we know is from the source domain, that remote spectra that we know is in the remote domain, and translate it back to that higher resolution lab domain. And I like this because it kind of looks like the generated spectra is like shrink wrapping to the output result that we're looking for. It's filling in the lost details. So we are essentially, it's not super resolution, but we are essentially going from something that only has 16 dots of information to something that has 156 dots of information, simply because it knows what data looks like in each of these domains and thus how to translate between them. And this is what several examples of that look like. And you'll notice that at the bottom here, some of them have failed to kind of hit the mark in terms of their overall reflectance. And that's kind of an important issue that we had with the model starting off that we're hoping to improve by giving it more diverse kinds of spectra to learn from. We think that the data set that we have is actually still too small to be able to build a fully diverse representation of the spectra. And instead, it's hyper-focusing on the average. And so we're working on things like synthetically inflating or decreasing the amount of data that you have in different, abundance classes. I think that decreasing the amount of data could actually work better in some situations because you're effectively, with a GON, the amount of data you have only goes so far. But in reality, how well it represents those domains is extremely important. So it performs well with the average spectrum. Doesn't do too great with a outlier or something that's unique to the domain in interest, right? And so we may need to do something to address the overall reflectance. But following the methods suggested in papers by a team called the Computational Science Initiative, which is Huang et al. And Torbanov et al., we added a UNet Vision Transformer 2-cycle GON. And so what this is we use a Vision Transformer bottleneck, which is a self-attention transformer mechanism, which models the global dependencies and the long-range relationships, right? So when we say long-range relationships, we mean, what does the overall spectrum look like? What does the general macro scale geometry or feature look like, as opposed to what are the details of that feature? That's what we mean when we say long range. And so what it's doing is we're essentially compressing the layers. And so we're keeping the global information, we're keeping the larger context while compressing those finer details in a bottleneck, right? And so traditional convolutions have local receptive fields. They're really focused on a window, whereas the VIT is going to cross all of the different bands, all of that context. And this is also much more efficient at training because you have that self-attention mechanism, right? And so you also need to introduce skip mechanisms to this bottleneck so that you can still maintain that that high resolution or fine details, the fine features, right? So they allow those low-level features from the earlier layers to bypass that VIT bottleneck and thus reach the decoder. So we're preserving the nuance of the spectra as opposed to the broader shape of it. And that maintains the finer details. It makes for clearer images. And it also means that we have shorter gradients, so they're less likely to vanish. And you'll notice it's significantly faster. You might have missed it. So this is the same model now with that the UNet VIT, and it's roughly 5 times more efficient. It ran for 500 epochs because we didn't expect such an improvement. Only 50 were needed. And in both directions, we have essentially the same accuracy, just significantly faster. And you'll see that we do, unfortunately, still have that overall reflectance problem because it's likely, like with a lot of machine learning, it's likely because of the input data, not because of the model architecture. A lot of machine learning is, curating your data, not your model. Right? So it still struggles with those same cases, and this is what we're exploring right now. Now you can compare them side to side, even though they are still struggling with that overall reflectance. You can see that significant improvement in speed. This is, you can see the actual difference there on the bottom as they kind of form to each other and essentially match in their accuracy. So next I want to go into the poster that we made. We presented this at LPSC. It was approved for public use and all of that. If I can... Okay, so this poster was presented at the Lunar and Planetary Science Conference, and the original work supported by the NNSA Defense Nuclear Non-Proliferation Program. Dude, I said non-proliferation for like 3 years straight, and I'm thinking back to so many different situations where I looked like such an idiot. And I only recently realized I'd been misreading that, and now I can't like unlearn. Anyways, so this looks like a mess, but I'm going to do my best to kind of walk through it in a way that hopefully makes things a little bit more clear. I'm going to go ahead and grab that. And we're going to focus on this first, right? And so what I'm going to do, so this is just a roadmap of the model architecture itself. How do I get rid of you? How do I get rid of you? A roadmap of the model architecture, right? And, what we're going to do here is we're going to follow that path that we were doing with the ducks, just with spectra. So we're going to start with, let's say we have our real remote domain spectra right here, all right? And so what we're going to do is we're going to translate that remote domain spectra to the lab domain, right? Actually, you know what? It might be easier if I start from this direction. You have your lab domain spectra. So we have a rock in the lab, and we might have some spacecraft data that we're pretty sure matches that rock. Let's go with that direction, all right? We have our real data. We're going to translate it to the remote domain using the lab to remote generator. So we're going to go over to here, right? And then in order to get cycle consistency loss, right, we're going to translate it back to the lab domain. And we have this A cycle. So then we do the cycle consistency loss. We can compare the real versus the cycle, right? And we can determine a loss to push that and train that direction of the model. Going in the other way, right? We can compare the real, right, to its identity version by taking the real lab spectra, placing it through the remote to lab generator. So it is expecting remote data, but it is getting lab data. So it should know not to touch it. It's like, oh, yep, that's correct. Leave it. So we're training it to identify what the correct domain is, right? And you can also do semi-supervision at this point, where you would basically optionally pair certain things between the two different domains, right? Let's go down with the discriminators now, where we can compare the real of the starting domain, the lab domain, to the translated version that came from the real of the remote domain. So we go across to here, right? And I'll change color maybe to make it a little bit more clear. We're here. We're going to go and let's start with identity. We're going to put the real remote domain data through the lab to remote generator, and we get the identity loss by confirming that it didn't change things. We take that real remote data, we put it through the remote to lab generator, and we get the translated lab data, right? So that translated lab data is the very same that we used to compare to the real lab data. And we use the discriminator at this point here to do that. We can continue on in that same direction that we started with, though, using the lab to remote generator, go back to the remote domain with the cycle and do our cycle consistency loss for that direction, right? And you can see, as I mentioned over here, we have the remote discriminator here, which can compare the real and translated for the remote domain. You can see the loss functions and where they're applied here as well. So you can see how this can turn into a cycle GAN as you go through each one of these loops. Taking us back to the actual poster, all the math is here. Ignore that. I want to go into the VIT and the UNet a little bit. So you might notice, why is this called a UNet? Because it's a U. So you have the inputs over here on the left and the outputs over on the right. As we mentioned, what we're doing here, right, is we are going through and encoding, right? And then we get to the bottleneck, right? The bandwise VIT at the bottom here. And then we do the upsampling, right? So we're downsampling and then upsampling, right? So we're decreasing the amount of bands we have, and then we're increasing the amount of bands we have. And as we do that, the lines here are skip connections, right? So we're skipping across the UNet in order to maintain those fine details. So as we go through the UNet and we go to that bottleneck, right, we're getting those long range details. And as we use the skip connections, we can get those finer details, right? This is what that VIT bottleneck block looks like, right? And so you have the learned positional embedding right after the reshape, right? And that goes into the multi-head self-attention mechanism, which then we use some different kinds of normalizations here for before we go into the feed-forward network, right? So this is derived from that paper that I mentioned that was developed by Dr. Turbanov, Yehu and Ren, and we've been working together, we've been working together kind of asynchronously because of their original work using the UNet Vision Transformer on a GAN style model. And now me and Indu here are collaborating on developing this same method for spectral data in particular, right? And it was cool to present this because there's a lot of skepticality justified with these kinds of techniques in science, especially when we talk about making inferences. And my goal with this poster and with talking to people from my community of science and not machine learning was to be like, hey, this is the tool in the toolbox. As long as you use it correctly, you can do really cool things with it. And this is sort of the example that I gave to people is, let's say, I'm going to try to pull this away from data so that it's easier for this context, but I would do this with regard to spectral data. Let's say you have, instead of a horse to zebra generator, you have a horse to duck. Right? And you're using that horse to duck translator in order to do some analysis on how they walk. Well, technically, if you learn something about how a horse walks, you could use that domain translation to use that data to figure out how a duck walks. But if it walks, if it quacks, you know what I mean? It's not going to work. You're not going to really get good inferences out of something like that because the data that you use to build the model itself is misguided in what kind of ground truthing there is between them. And I use ground truthing because that's the term that we remember for supervised learning, but what it actually is here is a manifold. And so the manifold properties. And so if we're talking about spectral data, the manifold property is, well, I'm observing, in theory, the same material. And so as long as I believe that they're the same composition, I can make inferences between those translated data about composition in particular, right? So in the same way that, okay, horse and a zebra, well, they have similar joints and linkages and so on. Well, okay, maybe I can make an analysis about the gait of a horse and relate that to a zebra pretty easily, but probably not a duck. And so that's where it's important, where you know what kind of data you're giving, you know what it's doing with that data, and then what it is going to infer about it, you need to figure out if that's actually valuable. It can translate anything to anything. Whether or not that's helpful is up to you. And the example I gave the researchers at this conference was, let's say you had visible to near infrared data and thermal infrared data, two entirely different regimes of the electromagnetic spectrum. You could technically translate between them, but there's no way that's going to be useful, right? Unless you actually have data from both that are all of the exact same material, particle size, environmental observational context, and so on, right? I think we talked a little bit enough already about the processing here. The processing of UV-Sigon itself here. This kind of explains the data set that we're working with. It mentions that we're pre-training and kind of going through each step. But I think that probably does it for describing UV-Sigon. And my goal here is to show that we can use all sorts of unique methods to deal with the problem of ground truthing, right? However, in the end, if we want to achieve this, if we want to start to get this play between modeling fundamental mechanisms and taking the inferences that we can derive from our observations, then what we're really going to need to focus on is collecting all the labeled data that we have across all these different contexts and getting them in a central location where we can access and analyze from them. And on the flip side, it's also really important that we figure out how to verify that inferences can be made in those different domains given an unsupervised method, right? So there's a lot that goes into machine learning that is mostly heavy on data preparation. And so going through these projects, it's sort of made me realize that the greatest barrier for the future of this technology in this field is going to be our databases and how we contextualize our knowledge from those databases and how we connect them, and quite directly where we store them. And so that's where the research that I'm doing discussing instrument inference architectures starts to stray from theoretical, here's the gap in the methods that we need to address, and more into, okay, here's the actual system that we could build, the infrastructure, the commercialize it, how could we commercialize it, so on and so forth. And so if I have the time soon, I'll tag that on the end of this, or we'll kind of set that up as a teaser where in the next kind of post I do of this, where I need to kind of get my thoughts out loud, we'll hone in on some more of this stuff and then talk about the fundamental mechanisms. Thank you again.